So today I'm going to be reviewing the first chapter of Database System Concepts. This book focuses on database design as well as the SQL language and designing schemas in general. So in 1.1, database system applications are covered. Not much is covered here besides two key terms and an example that will be persisting throughout the book whenever databases are referred to. So a database management system is a collection of data, also known as a database, as well as the operations, languages, and features and programs of how you access and use that data. And a database is just, of course, a collection of data. It doesn't even need to be stored on a computer. It could just be in a file cabinet. Now, the example used throughout this book is a university example. So a university would benefit from the use of a database as well as a database management system. For example, at a university there are many students they have to keep track of, many courses, students within courses, so relationships among these entities such as students and courses, as well as faculty, departments, salaries, basically everything that goes on at a university that needs to be recorded. So section 1.2 focuses on the purpose of a database system. So without a database system, the alternative is paper, which we have advanced. So basically it is the file processing system on an operating system, so a Windows or Mac or Linux file manager, uh, you know, um, and you could, there's a few problems with this. You could essentially call this a database, right? Because it's a collection of data. However, it's not, it doesn't have the primary intention of being a database. When you create a database, there's a few things you have in mind, a few things you want it to achieve, and a file system just does not achieve these things. And I'm going to share these things with you right now. So the first thing is data redundancy. In a file system, when you are creating two new files, it is highly likely that, well, when you create two new files and you can add whatever information to either file you want. There is no protocol that when you save the file, that if data exists in another file, it's already deleted and overwritten, right? Because each file is separate. So if you were using a file system to store data, you would have a lot of data redundancy. And this leads to data inconsistency. For example, if you have data in two different spots and you want to update the data or edit it, you might not know where all the data is located. Therefore, you may update only one file where the data is stored and not, for example, both files where the data is stored. Obviously, this is bad because then when you're retrieving data, you'll get inconsistent results. The next disadvantage is data heterogeneity, leading to data isolation. What this means is that files can be written in many different ways, right? You have many different extensions. You have PNG files, you have C++ files, you have Java files, you have normal text files, and data can be stored in any one of these. Most commonly, it'll be stored in a file that contains object code, from a specific programming language, or just the programming language file itself. And the problem with this is, you have different syntax. You could have data represented in two different data structures in two different programming languages, and this leads to data isolation. In other words, your data is not centralized and connected, right? It's isolated in different data structures and different programming languages, which makes it harder to access. So the difficulty in accessing this is if you wanted to, you would have to write an application program that goes through these different files that may be all different types of files and select the data you're looking for, which is obviously much too difficult, and a database would be much simpler. Now, there's also a difficulty in managing consistency constraints. Consistency constraints is a common keyword used in database systems, and that is basically a constraint to keep the database consistent. In other words, for example, to take the university example that the book uses, let's say you have a relationship among people taking courses and courses themselves, obviously, right? And if you add a course to a student's schedule, that course better be an actual course and not just some made-up course, right? So that would be a constraint to keep the data consistent, that every course you add to a student's schedule must be a valid course. So that's an example of a consistency constraint. And in a basic file system, it's of course hard to manage these because you would essentially have to write a new program to manage this, every new consistency constraint you add. It's not extensible. It's easy to write a few consistency constraints at the beginning, but if you want to add more, it requires making whole new programs instead of, in a database, just altering some syntax, right? Now, atomic data operations. Let's say you're editing a file and you, from terminal, okay? Whoops, sorry about that, guys. Let's say you're editing a file from terminal, and you're not done editing the file and your computer crashes, right? Now, most file systems just won't save the operation. But let's say there's a circumstance in which, part of the information you want to do gets saved and part of it that you want to do doesn't. Well, a good example is debiting and crediting. Let's say you have to debit an account, and of course, afterwards, you have to credit an account. So that's one transaction, right? Crediting of one account, debiting of another account. And let's say you credit one account, hit save, and before you debit the other account, your computer crashes. Well, then your data is in an inconsistent state. So this is what I mean by atomic, right? You have to do the whole transaction at one time. Okay, and then finally, concurrent access anomalies. So this is kind of hard to happen with a file managing system on a PC, but let's say you're using a virtual machine or something, right? And you could access two people basically had access to the files at once, right? And they're trying to update them. Obviously, a file managing system, if one person gets a value, changes it, and then gets it, but the other person got it before it was changed, then they're getting different data, right? So it leads to data inconsistency. And finally, security, right? Should everyone have access to read, write, and update these files? Now, of course, on a file managing system, you can implement this to some extent, but not to the fullest. All right, section 1.3, the view of data. So within a database management system, you have a physical level, a logical level, and a view level. Sorry, that should say level. Now, the physical level is how the data is actually being stored in the machine, the data structures used to store it in the machine, and all the inner complexities used that someone using the database won't see. The logical level is how the data is stored on the conceptual level for a particular application. Let's say, to take the university example that this book uses, you have let's say you want to add, you want the database to have courses, okay, and students, right? And courses and students have, different things, maybe a course ID, student ID, course name, student first name, student last name, student birthday, right? They have all these different attributes. And this is the whole of your database. It consists of students and courses, for example. This would be the logical level, right? The physical level would be, the data structures that are used to accomplish this, such as maybe it could be an object, right? In an object-oriented programming language. And then finally, the view layer is, where you see the database represented as a table or in some sort of diagram. It doesn't necessarily have to be visual like that, but it is one abstraction further from the logical and physical level. So you can't necessarily see the structure, the exact structure and relationships among the entities in the database or how they're stored in memory, but you can see it as a whole. And of course, you can view a database in many different ways. Worries with the logical level and the physical level, there is only one physical implementation and logical implementation. Now, to give an analogy of this that the book uses, they use an object in an object-oriented programming language. So in your object, let's use, so at the view layer, you have an object cat, right? And the cat has different methods and different instances, instance fields, private members, public members, maybe some friend classes. And this would consist of the logical level, whereas the object itself is the view layer level. And the physical level would be how the object is actually put into memory by the compiler, right? How many bytes it takes up, how it's accessed, stuff like that. Now, of course, with the physical level and the logical level, you're going to have a corresponding physical schema and logical schema. And this basically just means what's your implementation of the physical level or the logical layer. Schema is basically synonymous with implementation in this context. Now you have a few different data models. Data models apply mostly to the physical level, but also to some extent the logical level. And it's basically how the data is structured. So you have a relational model, a relational data model, and that is basically a collection of tables where you have, a set amount of columns that represent different attributes. And so, for example, you have like a student table and a course table, and then a student ID column, a student name column, course ID, course name column. You have an entity relationship model, and this is basically where you have, an entity, multiple different types of entities and relationships among them, not necessarily stored in a table format. And of course, all of these models have their advantages and disadvantages. Then you have an object-based data model, which uses objects to store data. So you would have a student object, and every time you add a student, you would basically be making a new student instance. You have semi-structured data models, and the semi-structured means different instances can have different attributes of the same entity. So one student can have a student ID, but another student may not need the student ID and has a student name where the other one doesn't, right? So you have the same entities, namely students, but not necessarily the same attributes. And you have a network data model and a hierarchical data model. Those aren't used in practice too much because they're older data models, but basically a network model, is basically a graph or a directed acyclic graph implementation where you have, certain entities pointing to other entities, and a hierarchical implementation or data model would just be a tree data structure, right? Where you have one entity like apes pointing to a set of children such as chimpanzees and monkeys and whatever other type of apes there are. And also there is a good website that explains data models in more depth. I'll put the link in the description. And by the way, all of this information is very introductory because it is an introductory chapter, and all of this will of course be expanded upon in further chapters within the book. Going on to section 1.4, we have database languages. So there are two types of languages used to interact with the database, and that is a data definition language, and also known as DDL, and a data manipulation language, also known as DML. So for a DDL, part of a DDL consists of a data storage and definition language, and this is basically, they're used synonymously, and they're basically the same thing. And the DDL is basically what implements when you define a schema at the logical level for a database, right? I want, to store courses in one table and students in another table and yada yada, right? You would tell the database how you want to store the information with a DDL, right? You're like defining the data essentially, right? Now, in a DDL, you're going to have assertions and authorization. Well, not necessarily, but most DDLs and good ones have this. So an assertion can either be a consistency constraint or an integrity constraint. A consistency constraint is more user-defined, right? Like to add a course to a student's schedule, it must be a valid course, right? So every time you update students, the database on the interior is checking this against the courses table, essentially, right? Or the courses entity. And you, of course, using the DDL, specify these consistency constraints. And you also have integrity constraints. And two common integrity constraints are referential integrity constraints and domain integrity constraints. So domain is, let's say you specify a student ID has to be a string, right? And so obviously you can't put integers in there. So very simple, of course the user does specify this, but it's more, you could see it more as integrity, right? Integrity of the data versus consistency, right? Keeping it all consistent. So, and then referential would be, let's say, referential would be, where one thing has to correspond to another. So for like one student's ID, let's say a student ID is used in two places, right? In two places. One in the student definition and one in the enrollment for a specific course, who's taking it, right? So this would be referential just to make sure that student IDs are matching up. You also have authorization, right? Who can read, update, insert, or delete this data. So that's what the DDL covers, right? That's what you can do in a DDL, and the database management system will enforce these once you describe it in the DDL. You also have DML, and this should support operations like retrieval, insertion, modification, and deletion. You have two types of DMLs, procedural and declarative. Declarative also sometimes goes by non-procedural. Now, procedural DML is where you specify how the database should retrieve the data. Declarative is a little more abstract and user-friendly. In essence, you just say what you want, and the database will determine how to get that data to you, right? So for those of you who have used SQL or a DML in a programming language before, right, this is the equivalent of getting a table from a database, using a while loop to go through all the entries, looking for certain things, and then selecting them. Whereas in a declarative DML, you would simply just say, get this value from this table, right? You're not using a while loop to check through all the entries to see if it matches the one you're looking for, right? Now, a subset of DML is a query language, but these are often used synonymously. And the query language deals with the precise retrieval, insertion, modification, and deletion operations. Also covered in this section is the query processor and the data dictionary. Now, when you use a DDL to define the specifications of the schema or how you want your data for your application to be structured, this is all metadata, right? It's not actually being stored in the database, right? Only what you put in the database is being stored there. But everything you tell how the database to be structured is stored in the data dictionary. And as a result, when you try to insert data on the lower level, the database management system is looking at the data dictionary to make sure your insertion operation lines up, maybe with the consistency constraints you enforced on it with the DDL. You also have a query processor, and basically, it does what it says. It processes the queries you give it with the DML, which is, the retrieval, insertion, modification, and deletion operations. And of course, one retrieval or one modification could mean several steps, and it's the query processor's job to handle this seemingly simple operation and turn it into a lower level step of operations. All right, section 1.5, relational databases. This section did not have too much information. Basically, it said most relational databases, or let me remind you on what one is. It's basically a collection of tables, right, where each table represents a different entity. It's also known as a record-based database because you have, these tables which are basically records. Now, you have fields or attributes, right, like student ID, student name for a particular student. These are represented as columns. And SQL, Structured Query Language, that's the acronym, is a DDL and DML used for interacting with most relational databases. It's a non-procedural language, meaning it gets the information for you. You don't have to specify how to get it, which would be a procedural DML. Now, in a relational database, a disadvantage of it is you have the potential for duplicated information. You could have information stored in, two different tables, and it essentially doesn't need to be there. To give an example of this, let's say you have everyone's in one particular table. You have a budget as a column, and a subject as a column, and a teacher as a column, okay? And maybe the table name is called teacher. And, multiple teachers could be in the same departments which have the same budget, therefore duplicated information. There are many more instances, in fact, in most databases, where you could have duplicated information. In most data models, like a relational data model, one of the main goals is trying to eliminate duplicated information. And, partly because, a user is ultimately specifying how a database should be structured, right, on the higher level. It's sometimes unavoidable. Now, SQL is Turing incomplete, which means, if you're familiar with what Turing complete is, a Turing machine, it can't compute all the problems that a Turing machine can. For example, most programming languages are Turing complete, almost all of them. All you really need is some if conditions, some while loops, some variables, user input, stuff like that. But SQL is Turing incomplete, and that is why you most often need to use it in addition to a programming language. And since these are two different languages, SQL, along with most DDLs and /DMLs, need an application program interface. In other words, you need an interface from the programming language to the data manipulation language. And two common examples of this, I'm sure you use this if you use C++ or Java, is ODBC, Open Database Connectivity, and then Java Database Connectivity. ODBC is used with C++, and JDBC is used with Java with SQL, right? So that's how you embed SQL in these programming languages, and they would often be represented as libraries within the programming language. And then finally, you have the DML precompiler. Now, this is optional. It depends on how you implement the application program interface as well as the DML itself. But basically, within a programming language, an option for them to implement this additionary language like SQL would be to, let's say put a hashtag in front of every SQL statement, like in C++ preprocessor directives, right? And the precompiler would basically recognize this and then execute those SQL commands. Section 1.6 covers database design. More specifically, normalization and the entity relationship model. Now, normalization isn't covered basically at all in this section. It's more introduced, and it's introduced as this way of eliminating redundancies within your data model on the logical level, as well as making it reflect the application as best as possible at the conceptual level, right? For example, if you have like a cat table and a dog table, you don't want stuff that the cat does in the dog table, right? And they don't touch on how you do this. I'm assuming they will, of course, in a later chapter. So I won't tell you here. And they talk about the entity relationship model, mainly three different key terms: an entity set, relationship set. These are basically the set of entities and the set of relationships, pretty straightforward. And mapping cardinalities, which is how consistency constraints are implemented in the ER model. If you have a background in set theory, cardinality is basically how many items are in a set, right? You could say the length, right? And what mapping cardinalities means is essentially it checks, let's say you can only have, for example, one student or 5 students per course, right? If you're trying to add a new student to a course, it'll check the cardinality of the entity set for students, which is 5, right? And you'll say, oh, it's already exceeded, can't add it, right? Moving on to 1.7, which is data storage and querying. So this is on the low level of the database management system. It covers the storage manager as well as the query processor. And basically, these two things are really the only things on the physical level. So a storage manager processes DML, database manipulation language commands to file system commands, essentially, right? You say to update one data in the DML syntax, and it'll translate that to, the file system command on the native operating system, right? However, it does a little bit more than this in between those two steps, right? It may optimize how the files are stored and how they're being brought into main memory, etc. So within a storage manager, you have a few different parts. You have authorization, namely, is the person giving the DML even allowed to do their DML command? Are they allowed to read this file, this data file? You have an integrity manager, and the integrity manager basically forces consistency constraints in all the different relevant assertions. You have a transaction manager, and what that does is, this will be touched on in a later section, by the way, within this chapter, but a transaction manager performs one transaction, so maybe in the DML you say credit this account, debit this account. Well, that's one transaction, right? And the goal of the transaction manager is to, or one of the goals at least, is to do this atomically, to do the credit and debit in one step in case of a system failure. Now you have a file manager. What the file manager does is it is an implementation of how you're storing the data, on disk, right? Maybe the different data structures you're using, etc. Then you have a buffer manager, and what that does is it manages the interaction between RAM, your random access memory, and the disk. How, what to store in the RAM, what to cache in the main memory, to make the data retrieval as efficient as possible, because of course accessing disk data is tremendously longer than accessing RAM. It also covers the query processor, and a query processor has the DDL interpreter, so basically just an interpreter for data definition language commands, DML compiler with query optimization, so a compiler for the data manipulation language, and of course, like most compilers, it'll perform optimizations to make the queries as fast as possible. And you have the query evaluation engine, which ultimately executes the queries. Now, next section, section 1.8, discusses transaction management. So within transaction management, you have two managers, a recovery manager and a concurrency control manager. And what this does, the recovery manager makes sure all operations are atomic and the data is stored and never lost, right? If the system fails, you won't lose all your data. It'll stay persistent to when you turn back the machine, to when you, the system fixes itself or you turn on the machine, right? Because of course, RAM is volatile, and you don't want to have any data stored in main memory because it is volatile. So you want it all stored to disk, so the recovery manager deals with system failures, essentially. Then you have a concurrency control manager, which makes sure everything is thread safe. People are getting one thread versus another thread are getting the same data, and if one thread tries to change one piece of data while another thread is changing the same piece of data, you won't have a race condition, right? Someone won't win. It'll be only one person, one thread is allowed to do it at a time, for example. And also, just in the transaction management itself, not in any of these two managers, it has to make sure the data stays consistent. We're nearing the end here, so bear with me. Section 1.9, it covers database architecture. It also covers normal application architecture, right? So you have 2 or 3 tier application architecture. 2 tier being you have a client and server, 3 tier being client server database, essentially. Another way to people often split this up is presentation logic, which is the client, business logic, which is the server, and then data logic, which is the database. And of course, nowadays you see more and more business logic being implemented on the front end, which is faster. And so these are just 3 ways of having a application architecture. In regards to database architecture, and specifically, you could have a distributed database or a non-distributed database, right? You could have a database on one computer, or you could have a database spread across multiple computers. Now, in this section, they also cover some scenarios interacting with a particular database. They have a great image. Unfortunately, I don't want to show it because I'm afraid of getting copyright. So I'll just have a picture of it on my phone here, and I'll explain some different pathways through the diagram that they give. So let's say within an application, a naive user, which is synonymous with like a user of the application, someone who doesn't know what's going on, right? They go to a website, they click a form, they want to get some information right through the user interface. Now, also known as the application interface. Then this goes to the compiled program object code. Let's say that's stored in the query processor. So how the form is being interpreted, right? And this will go to the query evaluation engine, which will go to the storage manager and all the different parts of the storage manager. So the buffer manager, file manager, etc. The authorization and integrity manager, as well as the transaction manager, will communicate with the data dictionary. You have the buffer manager and the file manager communicating with the data itself. You have the application program object code communicating with not just the query evaluation engine, but of course the DML compiler and organizer. Another use case would be an application programmer who's writing data, right? They have an application program, it gets compiled and linked, turns into object code. Then the query processor, executes the DML queries with the query evaluation engine, talks to the storage manager, and the storage manager talks to the disk storage, right? So on the higher level here, you have 4 sections. You have users, who either want to just read data, write data, etc. You have the query processor, which has stuff like the query evaluation engine, the DML queries, DML compiler and organizer, DDL interpreter. Then you have the storage manager below that, which contains the buffer manager, file manager, transaction manager, etc. Then you have the disk storage itself. So you can kind of see this layered architecture going on here. And you could have interfaces between each layer, right? Moving on, data mining and information retrieval. This is touched on extremely briefly, and basically they say not too much more than data mining, which is the process of going to a database, executing many queries, often with a program, right? You're not writing each one of these queries yourself, but you're executing a program that executes queries itself and tries to find patterns within data. And they say, of course, this is semi-automatic in most cases because you have to pre-process the data, you have to put it into a form that the algorithm can take as input, and you have to post-process the data because the algorithm can give you many different patterns among the data that tell you different relationships, etc. And these patterns could be absolutely nonsense. So you have to figure out, oh wow, this pattern is a good one versus this pattern is a bad one, right? This doesn't really have to do with database management systems. It just has to do with databases in general, as like someone wanting to find patterns, using data analysis. Another data analysis technique is information retrieval, which is basically querying unstructured data. So that means querying data not in a database and forming a database out of it. So maybe going on the web, using like a web crawler, going to different websites, looking for keywords, extracting data, and putting it into a database. 1.11 discusses specialty databases. I didn't want to say anything about this section because it basically discusses stuff that has already been discussed within this chapter. And the last section is 1.12, database users and administrators. So we have a few different types of users. We have naive users, which are users, who use the application, right? They don't know what's going on. They interact with an interface like a website, right? You have application programmers who, maybe program the database, read it, write it, using the query language. You have and then finally you have sophisticated users and specialized users, and those are basically users. They're basically application programmers who don't make applications and are just using SQL to look through the database or whatever DML they use. And then finally you have database administrators, and they are basically in charge of defining the schema, making sure the schema is structured well, not having any duplicates, using different processes to make a good schema, such as normalization techniques, which I haven't covered, of course, but to remind you, normalization is making sure data is not redundant and structured well, essentially. They're defining the authorization of read and write updates, who can use it, and basically doing routine maintenance. So that's it. 1.13 covers history, not that essential information, just repeated. And 1.14 is a summary, which is essentially what I'm doing. Well, this is the end of the chapter, so feel free to end the video now. Briefly, I'm just going to discuss some other channel things. So basically, I plan to do this whole book, cover this whole book, database system concepts, on this channel, and just review each chapter like this. Make sure to leave a comment on the approach I'm doing here, or any other textbooks you would like to see covered. This is my first video, so of course it's most likely going to be the worst one. Hopefully they'll get better with time. And make sure to subscribe to see the rest of this textbook done. Hopefully you won't have to read it in class and you can just listen to these lectures, or study ahead, of course. And that is it. Thank you for watching. Leave a like, comment, subscribe. Have a good day.